At 6 p.m. is 6:02 now. At 6 p.m., two formula pages activate on Blackboard. So if you go to Blackboard now, you will see 2 pages of formula. They are in red. One of them is called MEP1 and MEP2. Those are the formulas I'm going to use for tonight. So please, everyone, download those and look at them as we go on, okay? All right. So we are going to be using this formula. Let me stop sharing. First, everybody okay? I'm going to begin to record now.
This meeting is being recorded.
All right, good evening, everyone. Good evening from New York, wherever you are, from New Jersey, wherever you are. So this is the second week. And like I was just saying a minute ago, I have uploaded 2 handwritten pages of formulas on Blackboard. MEP1, MEP2. So if you haven't done so, please download those, have them available with you, because that's what we're going to be using tonight, okay? And so let me see if I can show you one of the formulas. Okay, so you must all have this. Okay. Can everybody see this, the formula?
Yes.
Okay.
Yes.
All right. So this is, so these are, I call them the formulas for moments. And what are moments? Moments are, for example, Danny, if I say, Danny, can you describe me, Joseph Onochi? Well, Danny will say, Professor, you are 6 feet tall. No, you are 6 feet 5 inches tall. You know, you're very handsome face. Your chest is, barrel chest. And you are, 200 pounds weight. You really, fit. Your skin is dark. You have, thank you. Oh my God, you don't need to come to my class anymore. You make an A already. You have, really nice looking blue, Hollywood eyes. So everybody, if you hear what I've been saying, he is using some characteristics to describe me. My height, my weight, skin color, eye color, amount of hair I have on my head, and so on and so forth. So when we have a set of numbers, for example, when we have a set of returns, or a set of prices, or a set of numbers that represent GDP, interest rates, when we have a distribution of numbers, and I ask you, look at this very nice, list of numbers, distribution of numbers, pretty looking, beautiful, nice looking. Can you describe that distribution of numbers? How would you do it? Just like Danny described me with those characteristics, height, weight, and so on, moments are the characteristics we use to describe distributions. Okay, so from now on, anytime I give you an exercise, I won't even talk about it. I won't even ask you to, it's automatic. You give me the moments of the distribution, okay? Everyone, you give me the moments of the distribution. There are 4 moments of interest to us. There are 4 groups of numbers that are of interest to us. Just like when Danny was describing me, one group of numbers represented height, weight, skin color, and so on and so forth. Okay? So for moments, there are 4 of them. First moment, second moment, third moment, fourth moment. The mean, the average or the mean is the first moment. The second moment is the variance. The third moment is the skewness. And the fourth moment is the kurtosis. Why do we need to describe a distribution? Well, it's like me asking, why might Danny need to describe me? Well, suppose Danny is a recruiter. Danny has a business recruiting. For example, Indeed. Okay, Danny runs a company like Indeed. And Alec, you run IBM or somewhere. You call Danny and say, hey, Mr. Danny, I need to employ one person, for this job and this job. And you give Danny the characteristics of the person you want. You want a female. You want a female that is 6 feet, above 6 feet tall. So you want a lady, a dark-skinned lady or brown-skinned lady, more than 6 feet 2. So you give the characteristic. For certain reasons, maybe you need that person to do sales, or maybe you want somebody, the lady, to run a distance, whatever, for whatever reason, you need a female. So what Danny does is Danny looks through his list of prospective candidates. And Danny, because of the names, Danny cannot figure out who is a man, who is a woman, because we all use different names from different countries, and it's difficult for Danny to figure out who is a man or who is a woman, and who is tall, who is not tall, and so on. So Danny asks everybody to give
and update your WhatsApp.
Bring a description of yourself, or stand up, whatever. So that just by looking at the characteristics, Danny will say, that Joseph Onoche looks, maybe he looks a little bit like a lady, but he's not really a lady because, male, sex, gender, male, he said, and then height, Joseph Onoche is 5'11", so out. Now there's Lily, there's Jaspri there. So now I have the female. Okay, good. Okay, Alec, the CEO, needs a female. Okay, this person is exactly 5'9" or 5'11". This person is 5. But bingo, only one of them matches exactly what you need. You understand that? The same way when we want to make investments in Wall Street, we have IBM, we have Facebook, we have Uber, we have Alibaba, we have, wait, those are a few from China. Is Tencent a public company yet? I'm not sure. Okay, we have,
yes, it is, I think. Yeah.
Okay, so we have Tencent is the company that owns, what is this? Not WhatsApp. What is this?
WeChat?
WeChat, yes. Tencent is the company that owns WeChat. Sorry, I was thinking WhatsApp somehow. So we have Facebook, we have Tencent, we have Alibaba, we have IBM, we have Uber. So you have money. These are all public companies that you can invest in, but you want to invest in only one that, over the past 10 years has given average return of 10% per year, is the variance, is the volatility, is this, and so on and so forth. So you have your characteristics in mind. We know we are investing for the future, but you need certain historical performance, and so you're looking to invest in one particular, invest in one particular stock that has met that threshold of investment. So what do? You have in Shanghai Exchange, in Shenzhen Exchange, New York Stock Exchange, in CAC 40, in France, CAC 40, CAC 40, in in Straight Times of Australia. You have thousands of stocks to choose from. So what do? You describe each of them. You calculate all 4 moments and you say, bingo, 10 cents fits my historical performance exactly to the T. That's the one I'm going to invest in. Again, past performance is no guarantee of future performance, but it satisfies my requirement for past performance. Therefore, that's the one I want. You understand? So you can use time series analysis. You can use statistics to describe investments, just like you can use moments to describe investments and time series and distributions, just like you can use those characteristics to describe human beings, okay? So the formula I just gave you, each of those formulas will help us to be able to calculate each of those 4 moments. So tonight I am going to be calculating those 4 moments with a very simple example. Tonight, we're going to focus only on the calculations. If I have a few minutes, I will describe what the numbers mean, okay? But if not, please forgive me. On Thursday, I'll bring up the same examples, describe to you precisely what the numbers mean, and then I'll follow up with an R session on Thursday, okay? So whatever we are doing today, we're going to do on Thursday with R, and you see how easy it is. And whatever formula I use, I'll give them to you and have you, just replicate the results. Okay, everybody? Okay, my man Danny, you doing well?
Yeah, that last part you said you're gonna assign something to replicate.
No, so on Thursday I will show. Before Thursday, I'm going to, whatever I do tonight, calculations tonight, I will use R to do those calculations. I'll use the same numbers to try to reproduce the same numbers in R, and then I'll discuss it with the class on Thursday. And then when I finish, I'll give you the formulas I use. I'll give you the R program I use, okay, so that you can reproduce the same result. And then, but that would be my program. And as a professor, my programs are very inefficient. Okay, but I'll give them to you. You guys use them, and then, knock yourselves out. Make them beautiful, make them more sophisticated yourself, whatever, okay?
Thanks.
All right, but what I want to do in this class is you and I should be sharing a program. So I'll give you mine, but if you feel yours is better than mine, please share it with me, okay? And typically my students are way better than me in doing this. Initially, it's a little difficult for them, especially if you guys haven't used R before. But you guys, you pick up much faster than I do, okay? All right, so what I'm going to do, I'm going to bring up an Excel spreadsheet now. I have done all those calculations on Excel, and I'll point out to you which calculation I'm doing, and I'll ask you to look at the formula, okay? I gave you 2 pages of formulas. You have them, MEP1 and MEP2 corrected. You have them, and as I show you the Excel spreadsheet, I'll discuss with you what I'm doing. And then for each item I'm calculating, I will ask you to look at the formula that I used to calculate them, okay? All right. Any questions? And again, my students always hate me when I do this. The Excel spreadsheet I'm going to use, all you will see will be the numbers. If you notice, I have not posted the Excel spreadsheet on Blackboard, because if I post them, then all the wrinkly formulas I use will be there, and you just reproduce yourself. But I want you to see the numbers, possibly take a picture of my Excel spreadsheet, and try using those formulas you have with you. Try and do them on Excel yourself before Thursday, okay? If you want to. All right, so that is the setup now. Let me bring up the spreadsheet. No, that's not what I want. Let's see. All right, I see my Excel spreadsheet. Okay, are you looking at an Excel spreadsheet?
Yes.
Okay.
Yep.
All right. So this is all we're going to discuss tonight. How about that? It's really simple. Okay, so so I may ask you guys to just bear with me, take a picture of this spreadsheet, because this is what I'll ask you to reproduce yourself on Excel. Okay. So this is a time series. Why do I say that? Because this is time, today, time 0, time 1, time 2, time 3, time 4. So we can say that for IBM or for Facebook, whatever this company is, that I looked at its price today, $15 or $150, whatever. And then its price yesterday, its price 2 days ago, its price 3 days ago, its price 4 days ago. So this is a time series of prices. Okay? Why am I beginning with prices? Because when I begin to give you assignments to go to for example, a website like yahoo.com, and I ask you to go download stock prices, okay? You will be beginning with prices. Sometimes I'll send you elsewhere. You will not have prices, you will have returns. Okay, but always the most fundamental level of numbers, prices. So we're going to be beginning with prices. We have prices here. And then we're going to be calculating returns. So this next column, C, those are returns. Okay? Because this is time 0. What will be the returns? Now, we can look at it, we can look at these two in different ways. I can just say, let's assume that we began in time 0, it was 15, and then 10, and then 12, and then 23, and then 25. So we can, let's say we are starting at point 0. I haven't made a big deal out of this so far, but the way these prices are could be, I'm calculating it the way you will calculate it when you go to Yahoo, because when you let us think, for example, that this time 0 is December. Let's say it's January 1 of year 2000. Okay, this is quite important. Please, everybody, listen carefully, because the way I'm going to calculate the returns will be based on the fact that this is a history of numbers. That is why if you look at your formula page, the one you just have now, if you look at the first page of formulas I give you, look at the top. It says moments ex post. What does ex post mean? History. It already happened. Okay. So when I say time 0, time 1, time 2, time 3, you can think that these are all historical numbers. You can think that this is January 1, year 2000. This is January 2. This is January 3. This is January 4. This is January 5. So we are beginning at a point in time, and we are moving forward in time up till today. but all of them are historical numbers. Are you with me so far? Okay. It's okay if you don't understand what I'm saying, I'll repeat it, okay, later. But the way we are going to measure the returns will be here. We started in time 0. Let me see. I think somebody had a question. Yes, we are moving forward through time, historical. But so imagine that today is 2000 and is February 9, 2021. But we are beginning in January 1, 2000, and we are moving from then forward till today. So as of January 1, 2000, January 2 is the future. January 3 is the future. Exactly. So the returns, if you're looking at, those of you looking at the chart, it's P2 minus P1 divided by P. Actually, it's P2 minus P1 divided by P1. Okay? Okay. All right, so look at this number. This number, negative 0.3333. How did we obtain it? It's here, I'll type it, it's 15. I'm sorry, let me do equal to 15. So 15 minus 10 divided by 15. Okay, thank you. Who is this now? Thank you, Alec. Yes, so is it 10 minus, it's 10, I'm sorry, it's 10 minus 15 divided by 15. So it's P2 minus P1 divided by P1. Okay? All right. So I got it correct in terms of numbers, but I got the sign wrong. So let me go back and fix it. So this would be B32. So B30. Okay, let me do it again. Sorry. God, a professor shouldn't make mistakes like this. You see, I told you I felt like going back to sleep today. So it's this one minus this one divided by this one. Okay, so it's 10 minus 15 divided by 15. So beginning, even though we have all the numbers, beginning in year 2000, January 1, we are moving forward. We're moving from January 1, 2000, coming to February 2022. Okay, so that's how we calculate the returns. Okay. By the way, there are two ways we can calculate the returns. What we have just, what I have just shown you is percentage differences in price. Another way is to take natural log difference. So we shall be discussing that next week, okay? After this week. So in this class, I'll be requiring you to, from time to time, calculate returns in two ways. One way is percentage difference, which I just showed you, like this one. P2 minus P1 divided by P1. That's what I just did. The second way will be using log differences, natural logs. I haven't talked about this. I will assign you to read that in chapter 1. And then after Thursday, we'll be using the log difference as well as the percentage difference, okay? All right, so there are two ways we calculate returns, the log difference and the percentage difference. And they are, we use them for certain reasons that we shall discuss later, okay? All right. So here, so these are all the returns. So in other words, from time 0 to time 1, the return was in negative 33.33%. And then from time 1 to time 2, the return was a 20% increase. and a 91.67% increase, and then an 8.7% increase. And then what the average return is 0.2176, which is the sum of all the returns divided by 4. Okay, everyone? So that is moment number 1. That is the first moment. Everybody, please look at your formula sheet. Equation 1. That's just what I just did. That's 21.76%. Okay, everyone? That's the first moment. So later, we shall spend a lot of time interpreting those numbers in this class. What does 21.76% return mean in English? We shall be discussing that. It means that if you had invested your money at time 0 and you held that investment till time 4, on average, simple average, you got a return of $21.76%, 21.76 cents on the dollar without compounding, based only on the principal. No interest on interest. Yes? Okay. Because if you wanted to calculate interest on interest, then you calculate what we call the geometric average. I will show you that later. I don't want a distraction for today. Okay? All right. Was somebody asking me a question? I'm sorry, I messed this up. Okay, sorry about that. Okay. So that's the first moment. So that's moment 1. Wait, did somebody ask me a question? Okay. So this is the moment 1 on the formula. Yeah, where in Blackboard is the formula under course document. Thank you. Yeah, just ask the question and somebody will answer. I don't need to. Under course document. Thank you, Lily. Yes, so this is what we call holding period return, HPR. Those of you who took investment analysis 3710 before, if you notice, I haven't made a statement about dividends, because usually holding period returns are divided into 2 parts, capital gain and dividend income, yes? This is only capital gain. I have not included dividends. We shall talk about dividends later. I don't want to be distracted. But when I ask you to go to Yahoo, when I ask you, yeah, thank you. When I ask you to go to Yahoo, when you go to Yahoo, as you will see, there are yahoo.com, Yahoo Finance, there are several columns of prices. And I'm going to be telling you the exact column to choose, okay? We shall discuss that later. All right. Okay, any more questions? Let me see, somebody has a question. Yes, there's MEP1 and MEP2 corrected. Okay, so please download the 2. Those are the only 2 things you have in red color there. Okay, so let's now go to the second moment. I didn't mean to. So let's go to the second moment. So this is second moment. So remember this, all of you, again, this is Echo 4000, Echo 4051. You know how to calculate variance. The variance is the average of the squared deviations from the mean. So this is the deviation. So the HPR is holding period returns, made up only of capital gains, no dividend. HPR minus average. So this is my average. 0.2176 is my average. So this column, I just take each number here. I subtract from that number this average. So 0.55095 is this number, C32, minus, I fix this number, okay? Notice the $C$37, absolute referencing. You know what I'm talking about. So these are all deviations from the average. and then I square them, and then I take them to power 3, and then I take them to power 4. Because variance is the average of these. Okay? Everybody with me? Skewness is the average of the deviations to the power 3. Isn't that easy? Kurtosis is the average of the deviations to the power 4. So all these moments, what are they? They are really averages. But what are we averaging is the difference. Here, first moment, we're averaging the raw returns, the straight-on returns. Okay? We get the returns, we average them. That's the first moment. The second moment, we take that average, we subtract that average from each return, we square that deviation. So each of these are squared deviations. Each of these are squared deviations. We add them up, we divide by 4. That's the average. So the average of squared deviations is what we call variance. Those deviations, we raise them not to power 2, but to power 3. So this is power 3 of this number, the deviations. This number is this number to power 3. So we do it for each of them. We add them all up, and then we divide by 4. The average of the cube deviation, the average of that is called skewness. We do the same thing, raise the deviations to the power 4 for each time period. Add them all up, divide by 4. That's the average. That's kurtosis. You understand? So in statistics, that's all we're doing, is we're just averaging. But the name we give those averages will be different depending on what numbers we are averaging. You get it? Okay. Let me go back here. What is the unit of average return? It's percentage, 21.76%. What is the unit of this one? The variance is percentage squared. Isn't that messed up? And if I was working in dollars, this average would be in dollars, this would be in dollar squared, this would be in dollar cube, this would be in dollar to the power 4. Can you imagine, Lily, I come to your shop and I want to buy Coke, and I ask you, how much is this bottle of, I want to buy Coca-Cola, not Coke. I mean, you guys with dirty minds. I want to buy Coca-Cola. You know Coca-Cola? All right, so I want to buy, I'm sorry I said Coke, but I want to buy Coca-Cola. And I said, Lily, how much is this bottle of water? Lily says, it's, Professor, it's $5 squared.
That's a pricey Coca-Cola.
It's $5 squared, or it's $5 cube. So the point is that because we are going to be comparing all these numbers with the average and using them together, these units don't make sense to us. So if you have taken statistics, you will know that as soon as you get variance, what do you normally do to the variance?
Standard deviation.
You take the square root.
The square root.
So when you take the square root, you reduce the number to 1%, from 1% squared to 1%. Okay, so this standard deviation is a measure of volatility in finance. In economics, it's a measure of risk. Okay, but variance will also give us a measure of risk, but the unit of measure is in squared units. So that's not appropriate. Yes, sir. Yes. What do I do with that? I mean, well, Andrew, my buddy, I was looking for you, Andrew. It's so good to see you. Andrew, this is the kind of thing you and I would talk about. You know, there's a little bar next to Baruch College. After class on a Friday, I'll invite the whole class. Of course, I'm the professor, so I'm buying, and I'm buying responsibly. One drink for everyone, one drink every 2 hours. And then you listen to me for 2 hours and you don't say a word, you don't ask a question, and I talk, okay? So what do you do when you have standard deviation? What do you do when you have risk? Now, if you give me 1 year of your time, that's still not enough from 9 to 5 every day. Because now I have a measure of risk, I have a measure of return, the first 2 moments. I can then say, I want to invest in Wall Street. Which investment do I want to make? Which portfolio do I want to create? Now it's mean variance analysis. I want to create the portfolio that maximizes my average return, but minimizes my standard deviation of risk. How do I do that? I get into Markowitz efficient frontier. I get into capital asset pricing model, and I can teach you investment for 1 year. You understand, Andrew? Okay, so that's why those of you who took investment analysis, this is what we call mean variance analysis. So with measure of standard deviation and average return for every stock in Wall Street, every stock in the United States, I can say, let me create the best portfolio that gives me the best return and the lowest risk. And I draw the efficient frontier and I introduce my utility function, blah, blah, blah. You understand? So this is the beginning of investment analysis that I teach every semester. All right. Are you satisfied? Just a little bit for now, so I can move on, Andrew. Okay. Okay. Many of you already took investment analysis, right? If you took investment analysis, you know what I'm talking about. If you did not, that's okay. Go ahead and Google them. Some of you took 3710 and 4710. Yes, exactly. All right, awesome. All right, so okay. Thank you, Andrew, for that question. And I can say more as the class progresses. All right. Okay, so now, we have the first moment, we have the second moment, but once we get the second moment, we take the square root of that, we call it standard deviation, okay? Okay, guys? And something else we do is we take the standard deviation and we divide it by the average. Standard deviation divided by the average, and that is what we call the coefficient of variation. So those of you who did not take investment analysis, we call it coefficient of variation, CV. So standard deviation is a measure of risk in the absolute. This is a measure of risk relative to return, relative to average return. Okay, Andrew? Okay, so in finance, we have measures of absolute risk. We have measures of risk. We have measures of relative risk, risk relative to something. Coefficient of variation is risk relative to average return. Another measure of relative risk is what we call beta. Beta is risk of an asset relative to the risk of the market portfolio, a benchmark portfolio. So in finance, we have measures of total absolute risk, not relative to anything. We also have measures of risk relative to something. Okay, so when somebody tells me, Professor, I made return, I had this amount of risk, I have this risk, I am wondering what risk are they talking about? Are they talking about total risk, absolute risk, standard deviation, or what we call volatility? Are we talking of coefficient of variation, risk relative to average return? Are they talking about beta? There are so many measures, there are different things we use to measure risk. So in finance, we like you to be a little bit more specific. But again, because this is financial econometrics, if you have not taken those classes, it's okay. When I get to those numbers, I will describe them for you so you'll be aware. And whenever we need to use those numbers in class, I will define them properly, tell you why we use them, and then we go on, okay? But don't forget, this is an econometrics class. We're just using financial variables, okay? Okay. Yeah, so if the prices were based on S&P 500, correct? If the prices were, so for example, I say IBM's beta is 2.5. That means roughly, if I'm measuring it beta relative to S&P 500, then I'm saying on average, whenever S&P 500 portfolio gains 1%, my portfolio, my assets, my investment gains 2.5%. And whenever S&P 500 loses 1% on average, then my investment loses 2.5. Whatever whatever S&P 500 does, my investment does in the same direction by beta 2.5, okay? Either going up or going down. And Joseph, it doesn't have to be S&P 500 always, like you know. It could be relative to Shanghai index. So when somebody tells me beta, my beta is 2.5, I'm waiting relative to what? Relative to the CAC 40, CAC 40 in France? Is it relative to the NASDAQ? Is it relative to the Wilshire 5000? So when somebody says beta, you always have to ask them relative to what index portfolio, okay? All right, I'm sure those of you who took investments, you know that already. Joseph Joe, I know you know that, so, but I'm just, okay. So once we calculate the second moment, the variance, I'm sorry. Once we calculate the variance, there are two other things that come along with it that you can calculate. Once you get the variance, you can take the square root standard deviation. You can divide the standard deviation by the average to get coefficient of variation, CV, okay? Then skewness. Again, because skewness is raised to the power 3. The unit is raised to the power 3. If we didn't like raised to the power 2, we do not like raised to the power 3, okay? So once you get skewness, the third moment, I divide it by standard deviation to the power 3. Take a look at your formula page. Take a look at my handwritten formula. Under formula 3, the first equation is this one, skewness. Are you looking at it? The second equation there is the first one divided by standard deviation to the power 3. Okay? Now, on Thursday, many textbooks, because again, Danny, you said I have, rich crop of hair. I used to have hair like Danny. I used to have big one, really nice. Sometimes I chop it off. I go sell it. I make a lot of money. But then I began to study finance and econometrics, and I lost all of them.
I feel you, Professor.
Joseph Baghdad, my man. My man, yeah. So I'm sure if I ask all of you to show me your pictures, many of you feel me already right now. Okay. Why did I lose all my hair? Because I have read so many textbooks, it's not even funny. If you ever come to my office at Baruch College, you're going to say, Professor, and I will go into that. But the advantage of reading so many books is I see the terminologies that many books use. Okay? All right. Now, I will make this point again on Thursday when we do it on R, because I haven't checked what formula R is using for skewness. That's okay. I know, but I'm not telling right now, but we will tell on Thursday. When many books say skewness, what they really mean is co-skewness, coefficient of skewness. So please watch out. When many textbooks give you skewness, what they are really talking about is not this number. What they are really talking about is co-skewness. Now, everybody, please look at the formula. This skewness, what is the unit of skewness? Because we are raising the deviation to power 3, the unit will be percentage to the power 3. So it's like multiplying this number by 1,000. This number. So this skewness will be 43.05 times 10 to the power 3. So that's what this number will be. But because the unit is percentage to the power 3, what happens if we divide it by standard? What is the unit of measure of standard deviation? Does anybody know? What is the unit of variance? Is percentage squared. When
I
we
think
take
it's the same as the unit of return would be percentage only.
yes, so standard deviation is percentage. But when I take percentage to the power 3, what am I doing? Is percentage to the 3. So when I divide this one, percentage to the 3, divided by standard deviation to the 3, which is percentage to the 3, the result is a number without unit. Anytime you have a number without unit, we call it coefficient. Okay, so this is called coefficient of skewness.
Professor, can you repeat the last part, please?
Okay. Sophia, are you looking at the formula page I gave you?
Yes.
Okay, so if you look at equation 3 is sigma HPR minus average to the power 3. Is that correct? Divided by n. That is this number, skewness. The unit of measurement, because each of those returns, these are all percentages. This is 33.33%, 20%. So because of that, the skewness is really percentage to the power 3. Even though this is decimal, but if you change this to percentage, there's no number like 4.3% as skewness. No, it is 43 point or whatever. Multiply this by 10 to the power 3. So, but we cannot use those numbers. Any number with a unit that is squared or to the power 3 or to the power 4, we cannot use them. So we remove them. The way we normalize them is, if I take this number, you can do the calculation yourself later. Take this number, divide this by this number to the power 3. So 0.4498866. If you multiply this number by itself 2 times, you raise this number to the power 3, and you use that number to divide this number, you will get this answer. That is called coefficient of skewness. So look, the formula is F37, so F37, so that number divided by E40 to the power 3. So E40 to the power 3 is standard deviation to the power 3. So that is called coefficient of skewness. Okay? So this number, coefficient of skewness, is really what most textbooks call skewness. And that is really what many softwares call skewness. So on Thursday, You and I will use R to do all of this, and then we shall see, okay? And again, everybody in this class, please look at my formula page again, the first one that you're looking at. Look at formula 1. What am I dividing by? N, is that correct?
Yes, that's a number.
How about formula 2? What am I dividing by?
By N.
And again.
N. But in statistics, if I take a sample, I divide it by what? N minus 1, remember?
Yes.
Okay.
Yeah.
Okay. So in Excel, that's the difference between population and sample. Remember that from statistics? So here, I'm doing all these calculations on the assumption that these numbers I have, the price, the 4 numbers I have for price, or the 5 numbers, that it's an entire population. So when you do calculations with softwares, you have to determine, or when you read these things in books, you have to determine, are they talking about population of numbers or sample of numbers? Here, I'm talking only with population, okay? Because as you will see, for many softwares just use N instead of N minus 1, because suppose I ask you to go to yahoo.com and download 20 years of IBM prices, 20 years of daily IBM prices, day by day by day by day, for 20 years of IBM. I mean, whether you subtract 1 from that number or you don't, does it really make a difference? It doesn't make too much of a difference, okay? Okay, so I am not subtracting, I'm treating all of this as population, okay? All right. So let me move on because of time. The fourth moment is kurtosis. So what do I do? Because this has normal units raised to the power 4. What do? I convert it to kurtosis, coefficient of kurtosis. How do I do that? I divide kurtosis by standard deviation to the power 4. Exactly. Thank you, Andrew. So I divide the kurtosis. Sorry, I'm just messing around here. I divide this kurtosis by standard deviation, but before then, I take this standard deviation, I raise it to power 4, and I use that result to divide into this, and I get this. Okay? This number is called coefficient of kurtosis. Now, again, in most textbooks, in most softwares, when they say kurtosis, what they really mean is coefficient of kurtosis, is this number. But I am giving you everything. Why? Because I lost all my hair reading many, many textbooks. It can be quite confusing. So that's why I'm giving you all these numbers. So when you go to a new software or new reference or a new literature or new textbook, and they are talking about skewness, you have to bear in mind, what skewness are they talking about? Is it normalized skewness, which is coefficient of skewness, or is it normalized kurtosis, coefficient of kurtosis? There's also something called excess kurtosis. So when you calculate second moment, you do 2 other things in addition. When you calculate skewness, you do 1 other thing in addition. When you calculate kurtosis, you do 2 things in addition. And there are many reasons for that. Because, and you and I will be doing this a lot in this class, we want to find out if this distribution of returns comes from this, a normal distribution. Do you guys remember what a normal distribution is? A bell curve, right? Anyone remember? Exactly. So a normal distribution has coefficient of kurtosis 3. So I always subtract 3 from, so excess kurtosis is always coefficient of kurtosis minus 3. So if excess kurtosis is a negative, that means that those numbers do not come from a normal distribution. Now, can everybody please go to the second formula page I gave you, the second formula page? On top of that, do you see what I said? For a distribution to be normal, we must have two conditions, okay? The skewness must be 0. And please look at my spreadsheet. You see where my cursor is? A and D in bold. Not or. Are you with me? Not or. So this must be 0. And at the same time, this must be 3. Those two conditions must hold in order for the distribution to be regarded as a normal distribution. You understand, everybody?
So what conclusion are we coming to in this instance?
Okay. In this instance, this is not 0. This is not 3. But over the years, many students tell me, Professor, how do you, I mean, I have so many things to remember. How do you expect me to remember skewness 0, coefficient of kurtosis 3? I said, okay, statisticians have thought about that. So if coefficient of skewness is 3, and it's a normal distribution, if you subtract 3 from that, right, then excess kurtosis has to be what?
0.
0. So a normal distribution is that set of numbers that has coefficient of skewness 0 and excess kurtosis 0. So you don't have to remember 3. You can remember 0 and 0. Okay, but I will explain everything.
Fat tails.
It's fat tails, but I will explain everything on Thursday. Okay, I don't want to rush today. So today I'm just doing calculations. Okay, you forgive me for that? Okay, so yeah, that's fine. I love that actually. So by the way, when I say, if everybody please look up, if skewness is 0, this one, what must coefficient of skewness be? If skewness is 0, then coefficient of skewness has to be what?
0.
It has to be 0. So whenever I say skewness is 0, coefficient of skewness must also be 0. So a normal distribution must have skewness 0, excess kurtosis 0. Not either or. Because do you guys remember in statistics, you use two types of distributions? You use a Z distribution, that's a normal distribution, and a student T distribution. Remember T? A T distribution, yes. A T distribution has skewness 0, but excess kurtosis is 0 for a T distribution. A T distribution has fatter tails than a normal distribution. Are you with me? So those two conditions must hold. Must hold. Skewness must be 0 and excess kurtosis must be 0. Look at this. Look at the formula page I gave you, the second formula page. The first 2 lines we set those conditions for you. Danny, you are raising your hand?
Yeah, I was just curious. Going forward, when you bring up skewness, are you talking about the textbook language, which is coefficient of skewness, or are you talking about the other skewness? The
We
points
shall
that.
let us settle that on Thursday. How's that?
Okay.
Okay. Just one final thing. You guys, you remember from statistics that if I want to measure, can anybody tell me what is wrong in this statement I'm making? I come to Baruch College. I want to measure the average height of students at Baruch College, right? But I go the wrong way and I go to the basement. I go to the to the second level of the basement, to the basketball arena, and I take a sample of 45 students playing basketball. Exactly. Thank you. Thank you. Okay. So I could take the wrong sample, even though Baruch students are 6 feet tall, but on average, but then I could take the wrong sample and I'm only measuring basketball players that are taller than 6 feet. So how do we correct that in statistics? We take a random sample, and then after taking a random sample, what do? We do hypothesis tests, yes? Okay, we do a hypothesis test to say, does this sample belong to the, okay, we're looking at this, all these numbers, average and standard deviation from this sample. How much does it represent the population to a 95 degrees of confidence? So what do? You take a sample, you measure the sample statistics, and then you compare that to the population statistics, or you measure the p-value. You remember that from ECHO 4000? Okay. When we want to see if something is normal, we look at the skewness and the excess kurtosis. If they are not zero, before we make a conclusion, we test hypothesis quickly. Okay? But how do we test hypothesis? Is something we calculate a sample statistic, just like you calculate a sample Z or sample T, and then go look at the back of the book for the critical value. Here, we measure something called the Jacques-Berat statistic. Everybody, can you please take a look at the formula page? I gave you formula page 2. Look at towards the bottom, you see where I said JB statistic. You see that? JB statistic. How do we measure that? We measure the coefficient of skewness, we square it. We measure the excess kurtosis, we square it. We divide the excess kurtosis by 4. We add it to the co-skewness, and we multiply everything by n divided by 6. That statistic is called the JB statistic, the Jacques-Berat statistic. And then we compare that sample number to the critical number from the distribution. And then we make our conclusion. And usually, if the sample statistic is smaller than the critical value, we say we accept the null. We cannot reject the null. And the null hypothesis is of normality, normal distribution. Okay, so this Jacques-Berat statistic is the statistic we use to test for whether the distribution is normal or not. And that distribution is not, and the distribution, this number must follow a particular distribution we call the chi-squared. If you look at the bottom of the second page, I have written what I mean by chi-square. CHI square is a chi-square distribution. But when we do calculations on Thursday using R, which we will not worry about chi-square and everything, we shall just measure the p-value. And you remember from ECHO 4000 that if you want to test your hypothesis to the 10% level, then your p-value has to be less than if your p-value is less than 0.10, then you reject the null hypothesis. You remember that? And if your p-value is larger than 0.10, then you do not reject the null hypothesis. But in this case, our null hypothesis is always that the distribution of returns come from a normal distribution. So if our p is very small, smaller than our level of significance alpha, then we reject that null hypothesis. And if we reject the null, we are rejecting the fact that it's a normal distribution. So if we reject that, then we're saying it's not a normal distribution. If your p-value is large, then you cannot reject the null. That means you accept the fact that it's a normal distribution. Okay, everyone? All right. I just barely finished my numbers. Sorry, guys, I talked too much tonight. I'm going to stop here.
Professor?
Give me a second, okay?
Okay.
What happened now? I can't see myself. I can't see anything now. All right, let me stop. Don't save. All right. So let me stop recording.
The recording has stopped.
Okay. Sorry, I haven't taught a class in many weeks, so I'm still not too sharp in moving around. So forgive me. Yes, somebody had a question?
Yeah, I want to know, what does the Jacques-Barra statistic measure again?
Okay, so the Jacques-Barra statistic, okay, let me just bear with me a second. All right, so I'm sharing this. So look,
Yes.
the Jacques-Barra statistic, what does it do? I take skewness, right?
Yes.
And I take excess kurtosis. Are you with me?
Mm-hmm.
Now, just look here. Remember what I said. If our distribution is normal, then what will our
Zero.
Zero, and what will our excess be?
Zero.
So this will be zero, this will be zero multiplied by, so the Jacques-Barra statistic will be zero. So if the Jacques-Barra statistic is zero, then it's a normal distribution. But sometimes we observe something is not zero, but it is still a normal, right? And that's why we use confidence intervals. Remember that from statistics?
Yes.
Okay.
Yes.
So in my spreadsheet, even though my Jacques-Barra statistic was not zero, but it was small enough compared to the interval, confidence interval I built around this to fall within the interval around zero. Yes?
Yes, oui.
Okay, I'm sorry.
That's French.
I was talking to French people this morning. Yeah, actually, beginning next week, I'll be teaching 2 classes with students in France.
Professor, I also had another question from one of the handouts.
Okay, but hold on a second. So you understand what I just said, right? Okay, so because the Jacques-Barra isn't zero, but it's small enough. But how small is small? We have to compare it to the critical value. And the critical value we get using this distribution, we call it a chi-square distribution with 2 degrees of freedom, okay?
Mm-hmm.
So this will be, if I'm testing for 95% confidence, this alpha will be 0.05, and my distribution, my degree of freedom is 2. So I look at the back of the statistics textbook. There's a T distribution, there's an F distribution, there's a Z distribution, there's a chi-square distribution. Are you with me? So you look at that, and so you have the critical number, and then you have the sample number. And if the sample number is very small compared to the critical number, then you cannot reject the null, which is what happened here. But in the future, we will not be messing with chi-square. We will just calculate the p-value. Okay. What's your next question?
So my next question is about the handout that you distributed via Blackboard.
Which one?